Alright, welcome back. So in this video we're going to be going over, as it pertains to derivatives, the chain rule. Up until this point in time we've gone over the power rule, gone over the product and the quotient rule, we've gone over some trigonometric derivatives, higher derivatives, and they've conveniently always worked out at face value. Okay. Trig derivatives, all things considered, right, if we have something like sine of x, right, technically it's invoking the chain rule, but we don't necessarily bring it up for our authentic trig functions. If I had made the sine of x to the second power, now I have an instance of the chain rule. So you might be asking, what's the big deal? But we're going to utilize the chain rule whenever we have something called a composite function, which is a function within a function. So we have, g of x that's located centrally inside of f of x. And what the chain rule says is if f and g are differentiable, then the composite function f of g of x is differentiable, and its derivative is equivalent to the derivative of the outside, still composed with the inner function, times the derivative of the inner function. Okay. And our first example is going to be actually with one of our trig functions, so you can understand quite quickly how we took that for granted in our trigonometric derivatives video. Make sure you're regularly consulting the chain rule as we go through these. So if we wanted to, if we were tasked with calculating the derivative of cosine of x squared, let's just refresh. The derivative of cosine of x is negative sine of x. Okay. And before I had even written down, our theorem for the chain rule, I had said we have an instance of the chain rule here that we don't necessarily need to pay homage to. The outer function is cosine, which we derived as sine, still composed with our inner function. But if we went to take the derivative of our inner function, x, it's really just 1, and we don't really need to ever worry about instances like that. But notice here, right, we have the derivative of cosine of x squared. So with this being our outer function, right, we have the derivative of our outer function still composed with our inner function times the derivative, which is 2x, and if you wanted to be thorough, we could have done a rewrite as such. Okay? So once again, as I've said in numerous other videos, derivatives are an extremely rote procedural task. Chain rule can be a little unfamiliar, but as soon as you get into this habit of identifying outer and inner functions, let's say we have something like this, I wanted to take the derivative of, okay, first off, work with everything in exponents, so let's actually rewrite this as x to the 4th plus 1 to the 1/2 power. Okay, so our outer function is the square root, which is represented by the 1/2 power. Our inner function is this expression x to the 4th plus 1. So if my outer function is really acting like a power rule, right, I'm going to take the 1/2, so y prime is equal to that 1/2 now becomes the coefficient. I subtract 1 while maintaining my inner function times the derivative of the inside, which is 4x to the 3rd. Once again, you can leave here, but if you want to simplify, you're more than welcome to. 4 divided by 2 is 2, 2x cubed over the square root of x to the fourth plus 1, which is equal to y prime. And to conclude, yet another short video on derivatives, because less talking and more practice and application. We don't need the smaller arrow now. We have general power and general exponential. Right, so assuming that our function is differentiable, so we have g of x to the n, like we just did with our square root function, right? We had an inner function that was raised to the 1/2 power, and very similar to what we had just discussed, right? So we're going to take the exponent, it's going to become the coefficient, we're going to leave the inner function as such, n minus 1, you can't see there, but we must also multiply by the derivative of that inside function. And you might be wondering, well, why didn't we have to do that before? Well, we did and didn't. Right? Because if I took the derivative of something like x to the third, well, the 3 became the coefficient. I subtracted 1 off the exponent. And when we go to derive x, it's really just 1. Right? So, baby steps before we get to something a little bit more complex. And the same holds true for an exponential. And I've definitely done this in a previous video. I always jump the gun with it. But more often than not, people always assume that x is stuck, fixated. Remember, x is actually a function itself, so let's give it the credit that is due. Right, the derivative of e to the x was e to the x, right? So we're going to keep this structure as is. But we're also going to multiply by the derivative of g of x, right? Whatever function represents our exponent for Euler's number. And if we were to calculate the derivative of something ridiculous, like e to the cosine of t, we keep this as is, and then take the derivative of this, which is simply negative sine of t. And that's all, folks. The chain rule in a nutshell.